Hi everyone. In this video I'm going to talk about how to find derivatives using shortcuts. Our previous method for finding derivatives is very labor intensive. It requires us to take the derivative according to a limit. So f prime of x, this is called the hard way or the four-step process. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. This is a very tedious expression to work with. I'll give you an example. It's simple. Like this is extremely simple to do with a shortcut, but nasty to do without a shortcut. So example, f of x equals x to the power 4. Horrible. F prime of x equals limit h approaches 0 of x plus h to the power 4 minus x to the power 4 all over h. So recall f of x plus h just means replace the arguments of the function, all the variables, replace all the x's with an x plus an h. So instead of x to the power 4, f of x plus h is x plus h to the power 4. Okay, it doesn't look so bad, but we have to expand that out. X plus h to the power 4 means x plus h times itself 4 times. So I'll do the first two and the last two. X squared plus 2xh plus h squared. And then if I FOIL out the last two together, I get x squared plus 2xh plus h squared. And now I have to FOIL those. It's a little bit worse than a FOIL. It's first times first, and then first times second, and first times third, plus second times first, second times second, second times third, plus last times first, last times second, last times third. You got to combine every expression in the first bracket with every expression in the second bracket, exactly one time for each combination. And we get x to the power 4 plus, let's see, I get 2 of those, another 2 of those, so 4 of those, 4x cubed h, and then plus 4 so that and that, match with that and that, okay. And then I have this one and that one. Plus 4, let's see, x squared h squared. Oh no, how many? We got more of those than that. See, I'm confusing myself. Squared h squared 6. So I get that one and that one. Yeah, 6x squared h squared plus and then 4, because I have 2x h squared and I get another one of those, so 4 of those, 4x h cubed rather, xh cubed plus h to the power 4. Yes, you can use Pascal's triangle if you know it, but you can do it manually as well, as shown there. Now we got to plug that in. Limit h approaches 0. And I'm going to show you a shortcut for all this, and some of you already know it. You've already read ahead or you've seen it previously. It's a pretty famous shortcut for taking derivatives of polynomial terms. Okay, then we get some cancellations. We get the x to the 4, the minus x to the 4 canceling. We can common factor an h from the top and cancel the h on the bottom. We end up with limit h approaches 0 of 4x cubed plus 6x squared h plus 4x h squared plus h cubed. After factoring an h from the top and canceling the h top and bottom. Now replace h with 0. We get 4x cubed plus 0 plus 0 plus 0. We get 4x to the power of 3. That wasn't very nice. What's the shortcut? How do I get that answer in one line? So maybe you can guess. F of x is x squared. The derivative of that, f prime of x, is 2 times x to the power of 1. F of x equals x cubed. If you take the derivative the long way, you'll get 3x to the power of 2. F of x is x to the 4. We just took that derivative, and we found the answer is 4x to the power of 3. And I'll put in one more here, that if we did it, x to the power 5, so x plus h to the power 5, FOIL, expand, subtract x to the 5, common factor in h, divide, set h to 0. What you'd get after doing all that is f prime of x equals 5x to the power 4. Based on this pattern, what is f prime of x if f of x equals x to the power of 6? What are we going to get? So ask yourself that. And f of x equals x to the power of n for any n. What's going to happen? So think about it. Pause the video and think about it. Look for the pattern. Look what's happening. Like, what's the relationship between the x to the 3 and the 3x to the 2? What's the relationship between the x to the 4 and the 4x to the 3? How's that relationship now then continued for x to the power 5? Based on that, make a hypothesis. What would happen for x to the power of 6? Please don't test that hypothesis. Foiling x plus h to the power of 6 out is not impossible to do, but you've better things to do. Whatever your intuition says the answer is probably right. I'll ruin the story for you and tell you what the shortcut is. Based on the definition of the derivative, we have the following shortcuts for derivatives. The first shortcut is that the derivative of any constant is 0. This is satisfying on several levels. Constants don't change. Derivatives are rates of change. So things that don't change don't have a rate. Things that don't change have a rate of change of 0. Perfect. Exactly what we want. The definition of the derivative matches that, by the way. Now here's the end of the story I just ruined. The derivative of x to the power of n. If you put any number, so it has to be a constant up there. If you take the derivative of that, x to the power of n, what you'll get is n times x to the power of n minus 1. What's happening is the old power is coming down in front, and the new power is 1 lower. So look back at the previous stuff that I wrote down. X to the power of 4, we took the derivative, the 4 came down, and the new power is 4 minus 1, 3. X to the power of 5, the 5 comes down, the new power is 5 minus 1, 4. It's a beautiful shortcut. It has everything to do with Pascal's triangle, actually. If you want to prove it in general, you can write out what the expansion is for x plus h to the power of n, and then it's the second term in that expansion that's going to survive. The first term cancels with the minus f of x part of the difference quotient, and then you have that first term in the FOIL, in the full expansion. When you common factor an h out, that term will no longer have an h in it, but all the next terms will have h to some power. So when you set h to 0, they're all going to disappear, leaving only that second order term. And the coefficient in front of the second order term is always going to be the power that was on x. It's really neat. But you don't have to prove it, you just take my word for it. The next shortcut is that the derivative of a constant times a function is equivalent to that constant being factored out multiplied by the derivative of the function without the constant. We will use this property so often we won't even think about it. It'll just be a reflex. And the one above as well. The next two rules state that if we take a sum or difference of functions and take their derivative, it's equivalent to the derivative of the first function plus the derivative of the second in the case of a sum, or the derivative of the first minus the derivative of the second in the case of a difference. Each of these is actually relatively straightforward to prove using this expression. The derivative is defined as the limit as h approaches 0 of f of x plus h minus f of x all over h. Let's go through a few examples of using this rule. So given on the left-hand side are a bunch of functions. F of x is 0, f of x is 5, and so on, and we're asked for the derivative for each of them. It says find f prime of x for each of these. So for the first one, f prime of x is 0 because 0 is a constant. For the second one, f prime of x is 0 because 5 is a constant. Okay, the derivative of negative 6, that's 0 because negative 6 is a constant. Pi is a constant. The derivative, 0. It's worth highlighting. Pi is a constant, it's not a variable. And then the last one, f prime of x is equal to 0 as well, because that's just a really ugly constant. Ugly constant. But still a constant. It doesn't have to be a nice constant like 7. It can be a horrible constant like the cube root of 6 plus 3 to the power of negative 2/3. Some weird decimal, whatever that decimal is. Okay, next rule is using the rule for x to the power of n. What happens is that the old power comes down and the new power on x is 1 lower than that old power. Now for the first one, it's actually something to watch, is that there's no power showing up on x. So what power is implied? It's a 1. If you don't see a power on something, you can always put a 1 there if you need to put a power on it. So f of x is x to the power of 1. That means that f prime of x is 1 times x to the power of 1 minus 1. So 1 times x to the power of 0. 1 times 1, anything to the power of 0 is 1. So we get 1. 1 is our answer. I'll just write that down. Note that a to the 0 is equal to 1 for a being almost anything. There is one exception, that's 0 to the 0. 0 to the 0 is undefined. Except in the limit, it might be defined. Anyway, okay, next one, we take the derivative. The old power comes down and the new power gets reduced by 1, so 6x to the power of 5. See how fast that is compared to doing it the long way with the limit definition of the derivative. The limit as h approaches 0 of f of x plus h minus f of x over h. Like that's the result of that calculation. Were we to actually do it, get out the paper, 2 or 3 pages and do it, well maybe not that long, but it's much longer than what just happened. All right, next one looks weird. That doesn't seem to fit on the page, does it? Our rule, this rule 2 is for x to the power of n, but that's not x to the n. Or is it? It is. It is x to the power of n. Because we can write a cube root as x to the power 1/3. F of x is x to the power 1/3. Now it matches the template. I can use the rule. The rule is that the old power comes down, so 1/3 comes down in front, and we have x to a new power. I'm going to calculate the new power over on the right-hand side. 1/3 minus 1 is equal to, we need to make common denominators, 1/3 minus 3/3, which is minus 2/3. So that becomes the new power on x. That's a perfectly good answer. I would take that answer, full marks, no qualification, no dithering, but the textbook won't. Back of the book, if you're checking your answers in the back when you're doing your homework, they won't leave that alone. They'll mess with it. I'll show you what they'll do. They'll say it's equal to 1/3 times x to the positive 2/3. So a negative exponent means you can bring the term down in the denominator and force the exponent positive now. So that x to the negative 2/3 becomes an x to the positive 2/3 down below, and then you can merge it with the 3 that's already down below. Okay, next one, x to the power of -4. Here's another place where you can get messed up if you don't follow the formula carefully. Notice that we're always making the power 1 smaller, 1 more negative. We're subtracting 1 from it. So when we bring this old power down, that part's okay, that part doesn't seem to cause confusion, but the new power is not -3. The new power is -5. So that was -4 minus 1 is equal to -5. We're subtracting 1 from the power. Right, and then the last one's everyone's least favorite. It's not just a fractional power, but it's also a negative power. So doubly bad. We'll take the derivative, f prime of x. The -5/7 comes down, and we have x to a new power. I'm going to calculate that new power off to the side. -5/7 minus 1. That's what we will put here once we simplify it. So -5/7 minus 7/7 is -12/7. And that'll be your answer. Right. Oh yeah, and it can be simplified as indicated on the next slide if you want. And that's optional. I should label that. Well, I'll leave it. I mean, multiple choice could be either of them, so you have to know. You have to know that those things are equivalent. Okay. We can do examples with rule 3, examples with rule 4. I hesitate to throw a proof on, but how would we prove one of these things? So let's say you want to prove rule 3. How would we prove rule 3? Not tested. I'm not going to ask you to reproduce proofs. It doesn't make any sense, especially not this year. So if f of x, or I'll call it g of x, I'll give it a different name. G of x is equal to c times f of x. Then g prime of x is the limit as h approaches 0 of g of x plus h minus g of x all over h. Now I'm going to replace g of x plus h by c times f of x plus h, just replacing all the x's by x plus h's. I'm going to replace the g of x by c times f of x. Okay, the next step, I'm going to common factor a constant out of the top. I'm going to common factor c out. So c times f of x plus h minus f of x all over h. Then I'm going to factor the c out in front of the limit using a limit property. You can go back to your notes on limits to look at what that property is. Okay, now we have an expression on the right-hand side, which is f prime of x. Proof that common factors can be brought, well, not common factors, factorable constants can be brought